Hello. Now we come to the second part of our project report. As discussed before, my project is on correlation coefficient maximization in image alignment problem using image registration technique. Now the idea is during the implementation of the MATLAB code, we have solely considered image alignment as our main problem and using image registration as our main tool. Now, as discussed in the previous video, the objective function is a nonlinear function on a parameter vector p. So our main objective is to find this parameter vector p. Now this parameter vector p is evaluated using an iterative algorithm which has been termed as forward addition algorithm. And now we will discuss the MATLAB code and we will walk through all the functions and we will see how it works. Now this function, this MATLAB code ankan.m is the main MATLAB code which calls all the functions and all other MATLAB code and then generates a final image which is backward warped and undistorted. Now the main considerations are these four transforms are the starting points. User can comment in and comment out any of the transformation and then transform variable takes up these sort of transformations. Secondly, see here you have a number of iterations which is predetermined by the user itself. Now the idea is, since this is an iterative algorithm to calculate the vector p, and at every step if it is not the optimum one, it is added with some small value of delta p to get an optimum vector p, the next step p. So now this process continues until and unless the optimum value is close enough or the delta p which is used is very small than a threshold. The threshold can be defined by the user. This is as the theory goes. Now by making a trial and error, we have defined a specific number of iterations by itself initially, because the idea is we can implement a small loop for this iteration and check for the threshold, and then it can update the NOI itself, but that will consume more resources of the CPU and we don't want to have that. We just want to stress on the fact of only using image registration technique to get the backward warped image. So we define the number of iterations at the initial. Number of levels. This is basically if you have an image which is very detailed and you want to divide the image into 2 or 3 or 4 or multiple layers, and then at every layer you treat the image separately. You perform the iterations on each of the levels and everything can be combined, and then the final image can be image registered and plotted as we will see in our examples. Now for example, we have mentioned 2 as a number of levels. Now this part shows that we take the image, it could be grayscale or it could be a RGB image. If it is an RGB image, it will check for the third column. If the third column is present, it will convert it to grayscale image. This is important because when we take a non-RGB image, it will do the iterations. This program will still run, but it will do the iterations 3 times more. It will take 3 times more time. So we don't want to have that. We want to just utilize the algorithm and just want to show how this image registration is useful in case of a flat grayscale image. Now here, this specifically doesn't do anything. It just shows how transformation works. For example, transformation, when it is a translation, it just moves the pixel by certain fixed value which is constant. If it is an affine, it rotates or it forms another sort of points which can be shown as this example. If it is an Euclidean, it is basically a sort of rotation which can be shown by pi by 60 degree of rotation and henceforth. So this is basically an example. This is not exactly what we defined, because user may want to define the type of rotation or the type of changes they want to make, but within the bounds of these four only. Now, when we actually have the image, we know what transformation we want to make, and then we define a region of interest, because as I said, the entire image should not be taken, because if we take the entire image, it will take a lot of time to converge, and then image registration will take place, but it will take a lot of time to actually show up the image. Now, these two important functions which are used, the most important is ECC.m. ECC.m, it does all the calculations. Like if you start from initial, this is TIC, which is very important because this is the thing, this is the time ticker which shows the amount of time it takes to converge. Now this is very important step also, because when you transfer all the parameters like image, the template, the levels, and all these stuffs, it will see that if any of these arguments are missing, the program doesn't go forward, because there is no point if you keep on doing the algorithm and you don't have number of level defined, or which is some garbage value. Now again, this will again check if the transform are defined in these four only. If not, it shows a transformation error, because it shows that the transformation has not been defined by the user. This part, it does again the same thing, like it wants to take the grayscale image. If it is not a grayscale image, it converts it to grayscale image from RGB image. This is pretty much important, because when you define ROI, as I said, we define ROI in this step. After defining ROI, if by mistake if some user is changing some of the parameters, or if you're tweaking around with the image, that might be changing the template of the image or the color schematics of the image. So this makes sure it doesn't happen after the transformation is done, or after the region of interest is defined. This does only the putting of the Gaussian filter, which just smoothens up. Now here, at each transformation step, as I said, it initializes the delta p, because since we are starting from point 0, we don't have a delta p. We have to start with some delta p, and then for each iteration we have to add the delta p with some previous values. So this is how we initialize delta p's with respect to the transformations. For translation, this is the format. For Euclidean, we have found this is format. For affine and homography, this is the format that we define. Now, as I said, if you go to the paper, you will find that the objective function will require the gradient of the image and the Jacobian of the warped image. This is purely mathematical, because if you define the objective function, if you want to minimize the objective function, it will correlate to maximizing the another function which requires gradient and Jacobian for mathematics. This part is showing if the image is too small, the algorithm should not work. Now this is a bunch of steps where basically the interpolation is occurring. The interpolation is nothing but this should come later on, because when we have all the parameters set, we have the optimized p, we can use it as a bilinear transformation to get back the original image. So this is pretty much, this is used for finally writing the final unwrapped image. Now, as I said, we compute the Jacobian, we compute the gradient of the reference vector, and we compute the Jacobian of the warp vector. These all things are looking pretty complex, but these are pretty straightforward, because this comes in the mathematics, and then we are just putting the mathematical equations on here. Now, update parameters. When we find a specific delta p at a step, we want to update that parameter by adding it to the previous step. So this parameter update, if you go to parameter update, it is pretty much simple and very small code. By every transformation, it will just take the delta p, add it to the var pin. Var pin is nothing but the previously optimized p vectors. The name is pretty confusing, but it is nothing but the previously optimized p vector, so that we can get the final vector. Again, coming back to ECC, so after updating, we'll get the warp because this forms a loop, and we'll get the warp at the end. Now, once the iteration is complete for one level, we go to another level, because as I said, if you divide the entire code into entire image into several levels, it is good for the sake of output, but it will computationally very costly. So this is how the code works. The image Jacobian is pretty simple. We have the mathematical formula in the theory, we just implement it. And next level, as we have discussed, warp Jacobian, as we have discussed. Now if we go on, if we run this code, you see we have chose affine transformation, and at the background it is doing something. See, level 2 iteration, something iteration has been done, level 1 something iteration has been done, and we have an elapsed time. This is the template image. This is actually the input image, but the ROI is defined like this. Now you see this and these are pretty simple, and this should be correlated with this and this. So if we have only this portion, we should have an algorithm to find this exact image, but it should not be deformed like this. So see the output like this, which is pretty similar to the template we have got. This is purely an application of the image registration, because ultimately it plots by using the bilinear transformation, which uses the p, and p has been generated by the iterative algorithm. Now, just for seeing some of the examples, if you comment this out, if you take this in and then run it again, see the code converges pretty fast in comparison to the previous one. It takes around 7 seconds instead of 10 seconds, and you see the output as it is. Again, if you go here, if you take this as an example, keep it as it is. If you change it to say 3, it will take 3 times the time. If it was 1, but since we are using the translation, which is very simple transformation, so it takes the least amount of time amongst all the 4. So this is pretty much the code. The flow of the code, if you want to refer to, it has been discussed well in details in the project paper. Thank you.